This is a follow-up video on this constant current source for milliohm measurement, and I've made some slight improvements, I think, to the device. After noticing that the dynamic behavior of this device in terms of voltage rise times is rather aggressive when you connect it to a device under test, and we don't want to risk damaging any sensitive electronics when we connect this to measure, for example, the milliohm drops in various components. So the first thing I did was I removed the capacitor that was on the input rail and then the capacitor that was on the output side of this LM317, which is providing the constant current. Simply because those capacitors are stores of energy, and we don't want that energy released into the device under test when we are simply trying to measure the resistance. The other thing I added was a 1 millihenry inductor on the output side, which is intended to slow down the voltage spikes, slow down the voltage rise on the output side when this current source is connected to whatever is downstream. So just to look at this once again, so we have the LM317, we have the trim pot, which can be used to trim to either 10 milliamps output or 100 milliamps constant current output. And then I have the 1 millihenry inductor on the output side. I've got two jumpers in the current position. It bypasses the inductor, and then if I move the jumper back, it will include the inductor. And in that way we can test how this behaves with and without the inductor and see how the voltage rise time changes. So let's do that experiment. I've got the output connected to ground, and then the positive lead is going to be connected to this 10 microfarad capacitor, just to simulate some component downstream that perhaps has capacitance, or whatever load downstream that's going to draw the current from this current source and cause some dynamic changes in the voltage. So I've got my scope set to trigger, and we're going to look at that when I connect the output to the capacitor. So here we go. Setting my scope to trigger mode, and try that again. Here we go. All right, let's look at that on the scope. There was a little jumping there from just when I hit one wire to the other. But you can see it's a very rapid rise time. It overshoots a bit to 13 volts. And the rise time is 30 nanoseconds, which is rather fast. So let's now repeat that experiment. This time I'm going to add the inductor to the output rail by moving this jumper. I'll reset the scope. Let's short out this capacitor so it's okay. And here we go. All right, I'm moving up to the scope again. So now we've got a rise time of 528 nanoseconds. So we've slowed down the rise time dramatically. I think that's just going to be a better way. You can see you've got some dynamic behavior there, but it overshoots to 13.5 volts. But the rise time is so much slower. That's going to be, I believe, safer for your device under test. Just avoid those rapid rise times, those quick pulses of voltage without the inductor. That was the purpose of this video. If people have comments or suggestions, I'm open to hearing them. So if you mark them in the comments, I'll be looking at those. Thanks a lot.